for an undirected graph, right? For an undirected graph. Fine. Covariance matrix. Covariance matrix of of random variables, or we can say vectors. Fine. Another example maybe um, Hessian of nonlinear functions. Fine, etc. Right. Now let's discuss that what's the nature of the eigenvalues of a real symmetric matrix. Fine. So nature of the eigenvalues nature of the eigenvalues of a real symmetric nature of the eigenvalues of the real symmetric matrix, right? So what will be those values? Fine. So so let u be um, a eigenvector of the matrix symmetric matrix A such that AU is lambda u, right? So let's define the complex conjugate of u as u star. So um, so and multiply that complex conjugate on both sides, then we'll get u star AU as u star lambda u. Fine, right? So what, as lambda is a scalar value, right? So we can get lambda as u star AU by u star u from the above equation, right? So what one can say about the lambda star? So lambda star will be u star AU whole star by u star u, right? Because its star will be same, right? So this A is a real symmetric matrix, right? And this A is a real symmetric matrix, so the complex conjugate of the u star AU will be the same as the u star A, right? Because A is the real symmetric matrix. So lambda star is going to be u star A star u star star by u star u, right? So this lambda star will be u star AU by u star u, right? Fine. So this is the same as lambda. Fine. So it is possible. It's only possible when lambda is, it's only possible when lambda is real, right? So this implies that, this implies that the eigenvalues of a real symmetric matrix will always be real, right? Fine. So okay, now next thing. So we define a symmetric matrix symmetric matrix A belong to this R n cross n domain as positive, positive, semi definite, definite, positive, semi definite. Fine. If for any non-zero vector x transpose ax is always greater than or equal to 0. Fine. So for all x belonging to n dimensional space, this will be greater than or equal to 0, right? So this implies that, as a shorthand notation, we write as the positive semi-definite matrix as this one, right? Fine. So the next immediate question which comes up is, what will be the nature of the eigenvalues of a positive semi-definite matrix? Eigenvalues of a positive semi-definite matrix. So what one can say about the eigenvalues of a positive semi-definite matrix? Fine. So let's suppose that lambda is the eigenvalue of a positive semi-definite matrix, right? Then what one can say such that this ax is lambda x for any non-zero vector, right? So we can take the inner product of ax with x, right? Fine. So this will be lambda x inner product with x, right? So lambda is scalar value and it's real also, right? So lambda will be coming out, inside will be left with x, this one, and this will be what, this will be x transpose ax, right? So lambda will be x transpose ax by x with x, right? So this x transpose ax, because it is positive semi-definite matrix, so it will always be greater than or equal to 0, right? The numerator will be greater than or equal to 0, and denominator is anyhow always greater than or equal to 0, right? Inner product of any vector with itself will be always greater than or equal to 0, right? So what does this imply? So this implies that lambda will always be greater than or equal to 0, right? Fine. So the next property is, for distinct for distinct eigenvalues of a symmetric matrix of a symmetric matrix A, real symmetric matrix A, the corresponding eigenvectors will be orthogonal to each other. Fine.